Hello, this is the Chapter 14 lesson. In the previous section we talked about the central limit theorem and mentioned that the central limit theorem is a very important theoretical tool and that many formulas are based on the central limit theorem. In this chapter we're going to see one such type of formula. These formulas apply to what are called control charts, which are a graphical tool for determining if a process, such as a manufacturing process, is changing over time. When we're manufacturing something, ideally we would want every single item that comes off the assembly line to be identical to every other item. However, that's not going to happen. There's going to be some natural variation within the product. And so one of the most important parts of manufacturing is what's called quality control. And that's where you monitor the quality of the items that are coming off the assembly line and looking for changes and making corrective action where needed. So to illustrate the idea here, let's look at this example. A baseball bat company manufactures bats that are supposed to weigh 32 ounces. So ideally every single bat that came out of the factory would weigh exactly 32 ounces. However, that's not going to happen. There's going to be some natural variation in the wood that's used to create each bat. The machines are going to change a little bit over time. Maybe the employees aren't going to do things identically every time. So there's going to be some variation within the bats. So suppose that when the manufacturing process is operating satisfactorily, bats weigh an average of 31.7 ounces with a standard deviation of 0.2064 ounces. So operating satisfactory means that the variation is within acceptable limits and we're happy with the quality of the final product. When that's the case, we have an average of 31.7 ounces with the standard deviation. So we're going to take this mean of 31.7 and standard deviation of 0.2064 to be our desired population mean and population standard deviation. Well, let's suppose that as part of our quality control on each day of manufacturing, we randomly select 5 different bats and weigh them. So here's some data from 6 different days of production. On the first day, the first bat weighed 31.4 ounces, the second one weighed 31.7, etc. Now notice that not all those bats weigh exactly 31.7 ounces. We have some a little bit below that, some a little bit above. There is some variation. The question we want to try to answer is the process in statistical control? Meaning, is that variation within the weights of the bats within acceptable limits, or are things outside of those acceptable limits? Well, this is a lot of numbers to look at. We don't like looking at a bunch of numbers. We want to draw a picture or a graph of what these numbers are telling us. So the first type of graph that we're going to draw here is what's called a runs chart. A runs chart is really just a special type of a time series graph that we talked about back in Chapter 2. Our horizontal axis is labeled observation. So observation 1 is the first bat on day 1. The second observation is the second bat on day 1. The sixth observation is the first bat on day 2, etc. And so we've got one dot for each bat, and they're connected with a straight line. And then we all have this horizontal line at 31.7 that we call the center line. That graphically depicts our desired population mean. So what we see is that the bats start off a little bit below the desired mean, and then we have a whole bunch that are well above the mean, and they drop down, and then they go back up again. So the fact that we've got so many bats in there in the middle well above average is an indication that maybe something's not quite right. So interpreting a runs chart like this, we're going to use 2 criteria, and then we're going to add a third criteria here in a little bit. So we say the process is not statistically stable, or in other words, it's out of statistical control, if number 1, there is a pattern, trend, or cycle that is obviously not random, or number 2, they're called the run of 8 rule. There are 8 consecutive points all above or below the center line. Well, looking back at that chart, we see that there are definitely more than 8 dots there in the middle, consecutive dots all above the center line. And so based off of that, we would conclude that the process is out of control. Well, to further analyze this data a little bit more, we need a couple of definitions. First, random variation. That's variation within the products that's due to natural differences in the products. There's nothing we can do about random variation. There's just going to naturally be some variation within the products. The other type is what we call assignable variation, and that's variation due to causes that can be identified, such as defective machinery, untrained employees, etc. Assignable variation we can control and we can do something about, and we want to eliminate that assignable variation as much as possible. Random variation we can't eliminate, but we can control and monitor. Now, continue on with our further analysis of the data. Instead of looking at the individual weights of the individual bats, we're going to look at the mean on each day. So on the first day, the sample mean is 31.6. That's calculated by simply adding up the 5 weights from that day, dividing by 5, and we get 31.6. On the second day, we add up those 5 weights, divide by 5, and we get a sample mean of 32.5. So we're going to analyze these sample means rather than the weights of the individual bats. If we look at those sample means, notice that they start off at 31.6, and then they increase 32.5, and then increase more to over 33, and then they drop back down closer to the desired population mean. So just looking at those numbers, there looks like maybe there's a trend. They start low, they increase, and they decrease again. But again, numbers are hard to look at. So we're going to draw a graph of what those sample means are doing. So here's our graph. Notice the horizontal axis we've labeled as day 1 through 6. We have one dot. The vertical axis is labeled sample mean. We have one dot for each day. And then we've got that horizontal center line again at 31.7. That's our desired population mean. So we see there on day 1 the sample mean was a little bit below the desired mean, and then it increased quite a bit those next 3 days, and then they decreased down closer to the desired population mean. So the fact that we've got 3 dots that are well above the center line is again an indication that maybe something's out of control. So continuing on that observation, a sample mean much different than the desired population mean would indicate the process is out of control. Graphically, that means if you've got dots that are well above the center line or well below the center line, that's an indication that something's out of control. Well, the next question we have to ask ourselves is just how much different does it need to be? Is a difference of 1 or 2 units enough, or do we need differences of more units? Just how much different does it need to be? Well, to try to answer that question, we're going to refer back to what we called the empirical rule, which we saw back in Chapter 3. The empirical rule said that in a set of data, about 68% of the values are within 1 standard deviation of the mean, and about 95% are within 2 standard deviations of the mean, and about 99.7 are within 3 standard deviations of the mean. Now this only applies to data with a normal distribution. Well, we can apply this empirical rule to populations with a normal distribution. In terms of populations, about 68% of the values in the population are within 1 standard deviation of the mean mu. About 95% are within 2 standard deviations, and about 99.7% are within 3 standard deviations of the mean. Well, 99.7% is practically the entire population. So practically all values in a population lie within 3 standard deviations of its mean. Alright, so what does this empirical rule have to do with sample means? Well, remember the central limit theorem that we talked about in the previous section says that if we take random samples of size n from a population with mean mu and standard deviation sigma, then x bar, the sample mean, has an approximately normal distribution. That means that our population of all sample means has a normal distribution, which means that the empirical rule that we just talked about applies to this population of sample means. Number 2, the mean of x bar is mu, the population mean. And number 3, the standard deviation of x bar is sigma divided by square root of n. So if the process is in statistical control, then practically all values of the sample mean should lie between its mean minus 3 times its standard deviation and its mean plus 3 times its standard deviation. So mu minus 3 sigma divided by square root of n, and mu plus 3 sigma divided by square root of n. So a sample mean not between these two numbers would be very unusual and indicate something is wrong. Our empirical rule says that about 99.7% of all our sample means should lie between those two numbers. If a sample mean doesn't lie between those two numbers, that would be very, very unusual and indicate something is wrong. So this leads us to our definition of what we call the lower control limit and the upper control limit. The lower control limit is simply mu minus 3 sigma divided by square root of n, and the upper control limit is mu plus 3 sigma divided by square root of n. Okay. So if we plug numbers into our formula here, our desired population mean is 31.7, sigma is 0.2064, and n, the sample size, is 5. That's because we select 5 bats on each day. And so we plug the numbers into our formula. There's our lower control limit, 31.4, and upper control limit of 31.98. So now we're going to add these lower and upper control limits to our chart that we just saw and form what's called an x-bar chart. So we start off with the same chart we had before. On the horizontal axis we have day, the vertical axis we have sample mean. We still have that line at 31.7. That's what we call the center line. And then we have another horizontal line at the upper control limit of 31.98, and then a horizontal line at the lower control limit of 31.42. And so what we see there analyzing this is that we have 3 dots that are well above that upper control limit. That's an indication that something's wrong, something's out of control. So now we can use this idea to add a third criteria to our interpretation. The process is not statistically stable if, by the third criteria, there's a point lying outside of the region between the upper control limit and the lower control limit. And so based off this third criteria, we would conclude that the process is indeed out of control. That's the same conclusion we came to by looking at the runs chart and informally analyzing this chart from before. So that means corrective action needs to be taken. Now exactly what that corrective action is, I don't know. But someone who knows about the manufacturing process needs to start looking at things and try to figure out what's going on. Why do we have these 3 sample means that are so much higher than a desired population mean? Now let's take a look at some other x-bar charts that illustrate a pattern. Here in chart A we have a trend up. Notice as we move from left to right, the sample means increase from about 15.6 up to about 16.4. So there is a pattern there. Sample means appear to be increasing. Chart B, right next to that, we have a trend downward, just the opposite. And in chart C, we have a shift up. Notice that the sample means start low at about 15.8, and then all of a sudden there in the middle they jump up to about 16.1. Part D, we have exact opposite, a shift down. They start high and then all of a sudden they jump down low. Chart E, we have one sample mean that's much higher than all the rest of them. Part F, we have one sample mean that's much lower. G, we have a cyclical pattern where we have kind of an oscillating behavior. They start near the population mean, they increase, then decrease, increase, and decrease. H, we have what's called an increasing variation. Variation is the difference between the sample means. Notice that they start off pretty close together, and then the difference between them increases as we move to the right. So any type of x-bar chart that exhibits any type of this behavior and it has some sort of pattern that indicates that things are not in control. Well, our next example is going to illustrate another type of control chart, one that we call a P-chart, which pertains to sample proportions rather than sample means. So suppose light bulbs are produced in batches of 100. So as part of our quality control, each bulb in 12 different batches is tested and the number of defects in each batch is recorded. So in other words, we test each bulb and record the number of bulbs that don't work. So here's some data. We got 12 different samples. The first sample we had 2 defects, so the sample proportion is 2 divided by 100, which is 0.02. Second batch we had no defects, so the sample proportion is 0, etc. The question we want to analyze is the proportion of defects changing? Is the proportion increasing? Is it decreasing? Or is there some other pattern? Well, if we just take a quick look at those sample proportions, it looks like maybe they're increasing. They start off pretty low and then by the end they get as high as 0.07. So it looks like maybe they are changing. But let's analyze this a little bit more. We're going to construct a P-chart, which is again very similar to an X-bar chart. Our center line, we calculate this, we call it P-bar, which is the total number of defects from all the samples combined divided by the total number of bulbs tested. So we add up all the defects, 2 from the first, 0 from the second, 1 from the third. That adds up to 33 total defects. Total number of bulbs tested is 12 times 100 because I have 12 samples of 100 bulbs. So 33 divided by 1200 is 0.0275. So there's our center line. Now to calculate our upper and lower control limits, we're going to use these formulas. First we have to calculate what we call Q bar, which is 1 minus P bar. This is very similar to when we talked about the binomial distribution. We had Q hat, which is 1 minus P hat. That's because this is all based off ideas pertaining to the binomial distribution. Our upper control limit is P bar plus 3 times the square root of P bar Q bar divided by N. Lower control limit is very similar except that we subtract instead of add. So the idea behind these formulas is very similar to the formulas for the X-bar chart. P bar is like the mean, and then the square root is like the standard deviation. So if we plug numbers into our formula, P bar, remember, is 0.0275, so Q bar is 1 minus that, 0.9725. And then we plug numbers into the upper control limit and the lower control limit. And you see there on the screen to the right how to enter those numbers into your formula. It looks rather complicated because there's a lot of digits there, but overall it's not too bad to enter. And so we get an upper control limit of 0.0766 and a lower control limit of negative 0.0216. So those mean that any sample proportion greater than 0.0766 would be very unusual and indicate that something's not right. Likewise, any sample proportion less than negative 0.0216 would be very unusual and indicate that something's incorrect. Well, let's make a quick observation. A negative lower control limit really makes no sense because you can't have sample proportions that are less than 0, and so we're going to set the lower control limit to 0. That's always going to be the case if we get a negative lower control limit. We simply set it equal to 0. Alright, now we're going to use our calculator to actually construct the P-chart. So in your calculator, first we need to enter the sample numbers in list L3. So remember, to enter data you select Stat, Edit, Edit. You get all your lists. And now you don't have to use list L3. You can enter them in L1 or L2 or whatever list you have available. I chose to use L3. And then in L4 we're going to enter the sample proportions. So there we see our data in the table, the samples 1 through 12. So in list L3 we simply enter the numbers 1 through 12. In L4 we enter those sample proportions, 0.02, 0, 0.01. And there you see a window of what your calculator screen should look like after you've entered all the data. Next, we're going to set up our graph of the upper and lower control limits and then the center line. So you press the y equals button, which is in the upper left-hand corner of the calculator. At y1 you enter the upper control limit, which is 0.0766. At y2 we're going to enter p bar, which is 0.0275, and then at y3 we enter our lower control limit, which is 0. So after you've done that, you set up your statistical plot. So you hit second y equals for stat plot, select the first plot, turn it on, you select the second type of graph, and then for X list you enter the name of the list in which you entered the sample numbers. In my case it was L3. And then Y list, you enter the name of the list that contains the sample proportions, which in my case was L4. Once you've done that, hit zoom 9 for zoom stat, and then you will get a graph, but it may not all completely fit on the screen. So to get it to fit better, hit zoom 0 for zoom fit, and when you're all done with that, you should get your screen that resembles this. We see 3 horizontal lines. The top one is the upper control limit, the middle one is the center line at p bar, and then the lower line, which is the same as the x-axis, is the lower control limit. And then we see our plots of the sample proportions. The horizontal axis there is sample numbers, the vertical axis is sample proportions, and this is what we call our p-chart. Now we analyze this and interpret it using the exact same criteria as we did for the x-bar chart. First of all, the process is out of control if there is a pattern, trend, or cycle that is not random. Well, if we look there at our graph in the lower right hand corner, there does appear to be a pattern. It looks like those proportions are increasing. The second criteria is the run of 8 rule. Notice that there are not 8 points, consecutive points all above or below the center line, so we don't meet that criteria. Third criteria, none of our points is above or below the upper or lower control limit, so we don't. The third criteria doesn't apply. However, the first one does. There is a pattern to those sample proportions, so we would conclude that the process is out of control. Specifically, it appears that the proportions of defects are increasing. So because they are increasing, corrective action needs to be taken. Looks like we're getting more defects per batch. That's bad. We want to correct that. However, let's make an observation. If the proportions were decreasing, then nothing needs to be done. If the proportions were decreasing, that means we're having fewer defective bulbs per batch, and that's actually good. We want fewer defects, so in that case it would be out of control still, but that's actually good. So nothing would need to be done in that case. Now in our last example, we're going to look at a third type of control chart that we call an R chart. We're not going to talk about the calculations behind it, but we are going to talk about interpreting it. So a company manufactures aircraft altimeters, and those are supposed to measure the altitude of an airplane. As part of their quality control, on each of 20 different days, 4 altimeters are tested and their errors are recorded. So they're tested by maybe putting them in a situation where they're supposed to measure an altitude of like 1,000 feet, and then their errors are recorded. So here's our data. On day 1, the first altimeter had an error of 2 feet. That means it read 2 feet too high. The second altimeter had an error of -8, means it read 8 feet too low. Third had an error of 5, etc. So instead of analyzing sample means or sample proportions, what we're going to look at is variation within the samples. So is the variation within the samples changing? So by variation we mean the differences in the errors changing. We had several different measures of variation from back in chapter 3. We had standard deviation, we had variance, and we also had range. Range was the easiest of those to calculate, so that's what we're going to deal with. So the range on the first day is just the largest error minus the smallest error. 11 minus a negative 8, that's 19. The second day the range is 8 minus a negative 5, which is 13, so on and so forth. So we want to ask the question, is there a change in the sample ranges? Well, if we look at those sample ranges from day 1 down to day 20, we see that they start off around 20, they more or less stay there, but then towards the end, starting day 14, 15, we get some around 30, and then by the end they get quite a bit larger. So it looks like there maybe is an increase in the sample ranges. Well, to further analyze that, we construct another type of control chart that we call an R chart. R stands for range, and we're not going to talk about the calculations behind this type of chart, but there you see the resulting R chart. We got our 3 horizontal lines, the upper control limit, the center line at what we call R bar, and then the lower control limit, which in this case is the same as the x-axis. And we have 1 dot for each sample range, and we interpret that in the same way. We look for a pattern, look for a run of 8, or we look for points above or below the upper control limit or the lower control limit. And so because you notice on that last day our point is well above the upper control limit, by our third criteria we would conclude that the process is out of control. And specifically it means that the sample ranges appear to be increasing. And because they're increasing, some corrective action needs to be taken. It means we're getting more variation within each day of production. That's bad. We want as small variation as possible. So some sort of corrective action needs to be taken. So that's it for the Chapter 14 lesson. The homework is posted at Course Compass.